All right, section 8.3, complex numbers, trig form. Actually, over the next few sections, we're going to see a lot of the same types of calculations come up, or at least a lot of the same similar processes. A lot of it's stuff that we've already done before in terms of like using the right triangle definition of our trig functions or the XYR definition of our trig functions. But what you want to be careful of is that even though we're going to be doing a lot of the same type calculations or similar calculations, you've got to watch your context. You've got to watch the language, the terminology that's being used, because although it may seem that we're doing something different because of the terminology that we're using, it's still going to be basically the same process. Right? So I don't want that to be confusing, which of course it can be. You're doing, like I said, you're doing basically the same thing, but calling it something different. So that's part of the issue to be careful of over these next few sections. Now, section 8.3 deals with complex numbers. You may remember from algebra, right? You talk about complex numbers, which come from the square roots of negative numbers, and you have that standard form of a complex number, that a plus bi format, right? And remember, the I represents the square root of -1, right? That imaginary unit. And so you're able to write these numbers that have both real parts and imaginary parts, right? Standard form a plus bi. Now, for our purposes, I don't care about the whole imaginary number thing. The whole square root of -1 does not come into play with what we're going to be talking about here. Our focus in this section is going to be on the complex numbers themselves and how they can be written. And we have this standard form, the a plus bi, which is what you deal with in algebra. We also have what's going to be called a trig form of these complex numbers. And so we're going to talk about that. So it's not so much about the complex numbers themselves and what they are, as it is about how you can express or write complex numbers. Now, there's a lot of different little topics in this section 8.3. So, a lot of different things that we're going to have to touch on with respect to complex numbers. There's going to be several little formulas that we're going to mention. So be prepared to have to memorize some formulas. Right? Most of them are pretty straightforward, I think. But, obviously, anytime we have to start memorizing a bunch of different little formulas, there's room for error there and wires to get crossed. So be careful. But again, it's all about context. You got to watch the question and identify, which formula do I need in a given situation. All right. So with these complex numbers. So for real numbers, you can graph real numbers on a number line. When we graph in the XY plane, right, that XY rectangular coordinate system, remember that both the x-axis and the y-axis are real number lines. So you can only plot real numbers within that xy coordinate system. Complex numbers, which contain imaginary parts, cannot be graphed in our regular real coordinate plane. So what we do is we develop a different coordinate system. Right? It's still going to be a rectangular coordinate system, but instead of using points of the form x and y, or coordinates x and y, we use points of the form with coordinates a, b. Right? So just as we can graph real numbers on a number line, complex numbers can be graphed in a plane. So we graph complex numbers a plus bi the same way that we would graph an ordered pair of real numbers. But instead of calling them x and y, we'll call them a and b, right? The real part and the imaginary part. So then instead of an x-axis, we're going to call that the real axis, and that corresponds to the real part of our number. And then instead of the y-axis, we'll call it the imaginary axis, right? So it's still the same rectangular plane, right, with the two perpendicular axes, but instead of calling it the x-axis, we call it the real axis. And instead of calling it the y-axis, we call it the imaginary axis. And so you can then plot these points, these complex numbers, in the same manner that you would plot an ordered pair. So 2 plus 3i, I could plot as the ordered pair 2, 3. So it's nothing different than what you would do just to plot an ordered pair in the rectangular coordinate system. Right? Remember what I said earlier, it's all about context. It's nothing different, nothing new. It's just the language and the context in which we're using it. So negative 3 minus 4i, I could indicate using that ordered pair negative 3, negative 4. We'll call that point B, right, located at that, or in that location. All right, so nothing different there. Don't read too much into that. Now, here's where things are maybe a little bit different. If you look at letter C, the number that we're plotting is negative I. Now, that's a purely imaginary number, right? There is no real part to that number. Or we could say that the real part is 0, right, with an imaginary part of 1, right, 1i. So we would plot this one as we would the ordered pair 0, negative 1 down here. Now, that should also make sense because if this is a purely imaginary number, then it makes sense that it would lie on the imaginary axis. Similar, letter D, the number 3, purely real number. Now, you could write that as a complex number with an imaginary part, but the imaginary part would be 0, right? Because there is none. So I could plot this, in the form of an ordered pair, 3, 0. But again, this should also make sense that that number 3 would be located there, which is on that real axis, right? Which is, again, just a real number line, okay? So it's all about context. You're still just plotting ordered pairs, right? Just in the case of the pure imaginary and the pure real, be careful there. An imaginary number is on the imaginary axis. A purely real number is on the real axis. Okay? Absolute value. You talk about the absolute value of a number or absolute value of a real number. The definition of that, we define absolute value of a real number to be the distance of that number from 0 on the number line, right? So, the absolute value of 3 is 3. The absolute value of negative 3 is also 3, because both of those are a distance of 3 units from 0 on the number line. Excuse me. Now, in these complex numbers, or in the complex number system, the idea of absolute value is a little different. It is still distance, but now we're talking about the distance of this point, or this number, from the origin in the complex plane. Right, so when we put it in the context of that xy, or in this case now AB plane, we're looking at the distance of that number a plus bi, represented by the ordered pair AB, from the origin. And if you notice on the left, I've got this letter Z used to represent this complex number. That's a traditional notation. This textbook doesn't use it, so I'm not gonna use it beyond what we have right here. That should actually be a Z right here, not a 2. But Z equals a plus bi, and then we're looking at the absolute value of that number. So the absolute value of a plus bi. Now again, since absolute value is distance from the origin, that's what I'm looking at here. Change this. All right. That's our distance from the origin. Well, we can put that right back into the same context that we've always used with respect to finding the length of the hypotenuse of that right triangle with legs A and B instead of X and Y. Right? And so this brings us right back to our right triangle definition, our XYR definition of our trig functions, Pythagorean's theorem in the case of a right triangle, a squared plus b squared equals c squared, where in this case, the c is the length of the hypotenuse, which is the absolute value of our complex number a plus bi. Because remember, the absolute value, that's a number. And so it's the distance in this case. So the way I have it written, you could use distance formula. It's the distance between the points A, B, and 0, 0, the origin. But again, that's nothing more than Pythagorean's theorem. So that's all this comes down to. So like we said again, nothing new here in terms of how we're calculating that value. We're just calling it something different. It's a different context, right? So that's pretty straightforward. I mean, if I want the absolute value of a complex number, then I'm just going to run it through this Pythagorean's theorem. And I've got the absolute value of a plus bi, and I went ahead and worked these out, save us a little bit of time going through this, do these examples. So I've got the absolute value of 2 plus 3i. A is 2, b is 3. So I'm just plugging it in. Square root of a squared plus b squared would be the square root of 2 squared plus 3 squared, which is the square root of 4 plus 9, or square root of 13. And that would be the absolute value of that number. The absolute value of negative 1 minus 2i, right? A is negative 1, b is negative 2 in this case. So I've got the square root of a squared plus b squared, which is the square root of negative 1 squared plus negative 2 squared. And that would give us 1 plus 4, or square root of 5. And that would be our absolute value. Okay? Now, remember, absolute value is always a positive value for the same reason that it is with real numbers, right? Because it's always measuring a distance, in this case, distance from the origin of the point a plus bi, or the number a plus bi. So it's always going to be a positive value. So if you take, for example, look at number 3, I've got the absolute value of 2/3 I. Now remember, that's a purely imaginary number. So that's going to be a number that's on the imaginary axis, a distance of 2/3 units from the origin. And whether it's a positive 2/3 or a negative 2/3 I is irrelevant. It's still 2/3 either in the positive direction or 2/3 in the negative direction, just like 3 and negative 3 have the same absolute value, right? Always wants to throw me back to the top. Now, here's the big part of this section. And this is the actual the main part of, or main point of our discussion. Because I mentioned earlier, the whole reason for, or the whole purpose of what we're looking at is to define another format or another way that you can represent these complex numbers. Instead of that standard form, that a plus bi form, we have this trig form or trig notation that can be used to represent the complex numbers. And so notice again, we're just making use of that right triangle, same old, where instead of x and y, we're using a and b. Our hypotenuse is still labeled as r, but remember, what is r? R is the absolute value of a plus bi, all right? And then we have our a value and our b value, and we're representing that as the point AB. And then with our right triangle definition, we've got the cosine of the angle theta in standard position as instead of y over r, instead of x over r, we've got a over r. I could then say that a would equal r cosine theta, right? Just rewriting, solving for a. We also have the sine of theta instead of y over r. We're just replacing y with b, so I've got b over r. And so I could equivalently say then that b is equal to r sine theta. All right, so it's just another use of that basic right triangle, or XYR, in this case ABR definition of our trig function, sine and cosine. So then this a plus bi, which is our standard form of the complex number, if we replace a with r cosine theta and replace b with r sine theta, I get r cosine theta plus r sine theta I, just making those substitutions. And you'll typically see it written this way, where they'll factor out the r and write it as r times cosine theta plus I sine theta. And remember again, the I there is the imaginary number. It's the square root of -1. That's what it represents. Okay? So that notation is still the same. This last little notation, this r cis theta, r cis theta, that's just a collapsed version of the r cosine theta plus I sine theta. Unfortunately, again, this textbook chooses not to use it. So on MyMathLab, you're always going to have to write these numbers out using this form. I'm going to write them using this one, just to save us some time, save us some space. But all that is, the CIS is a collapsed version of the cosine plus I sine, because theta is going to be the same in both cases. So it's just a shortened version of that. But again, on MyMathLab, you're going to have to do it this way. You're going to have to actually write it out with the cosine theta plus I sine theta. Okay? But I'm going to use the r cis theta to make things a little bit simpler and quicker for us. So then this trig notation for complex numbers. Right? So the a plus bi can be written as r cosine theta plus I sine theta, or r cis theta. R is, again, the absolute value, right, of the complex number a plus bi. Theta here is still called the argument. Nothing changes. It's still the argument of your trig function. And this notation, it also is called polar notation, or polar form of a complex number. Now, I don't want to use that terminology because in our next section, we're going to talk about polar coordinates and the polar coordinate system. And that's something different than what we're talking about here. So I don't want to confuse the two. But this trig notation, or trig form of a complex number, is also sometimes referred to as a polar notation. And we'll see why. I mean, that there's a similarity between the notations, but I don't want to confuse the two. So I'm just going to call these the trig form, and I'll save the polar notation for the polar coordinate system, which we'll talk about later. So, of course, now we have two different forms for expressing our number, or for writing our number. Switch back to my highlighter. Right. So being able to convert between the two forms. Right. In some cases, using the standard form a plus bi serves its purpose. In other cases, using the trig form is going to serve its purpose. And for our purposes, it's going to be all about the trig form. So all these little formulas that we're fixing to talk about, it's all about taking a number that's in standard form, putting it in trig form, and then using the formulas to do the calculations that we need to do. All right. So converting between the two forms. To convert a complex number from standard form to trig form, all right, so we're going from a plus bi to that r cis theta, or cosine theta plus I sine theta. We need to find r, and we need to determine theta. Watch the quadrant, watch the quadrant, watch the quadrant. As always, anytime you're identifying an angle, make sure I'm identifying the angle in the appropriate quadrant. Right? Now, you're going to know your quadrant because you have the standard form of your number a plus bi. And we're looking at that as an ordered pair AB. So the signs, positive and negative, of A and B, of course, will tell you what quadrant your number is located. So then we can just adjust our angle accordingly. Right? But that's not a new issue. We keep saying that anytime I'm finding or using information to find an angle, I need to be careful to make sure I'm finding it with respect to the appropriate quadrant. Right? So as always, watch a quadrant, watch a quadrant. So we're using r equals square root of a squared plus b squared. Right? We'll find our r value. That's our absolute value of our complex number. And then how you find theta, that you have your options here. I mean, once you find r, we can use sine theta equals b over r. We could use cosine theta equals a over r. Or we could use tangent theta equals b over a. Like, remember, b is taking the place of y, a is taking the place of x. So that's the same as y over r, x over r, and y over x. But you pick your poison. Doesn't matter which one you use. I typically use this one, and that's what I'm going to use just to get us a little practice maybe with some of those tangent values. Right? But you could use any one of the three. Doesn't matter. Parentheses, many angles could be used for theta. Of course, we tend to choose the smallest positive angle, and I'll point that out in a couple of the examples that we're going to deal with, because sometimes I can end up with an angle theta that's outside of our 0 to 360 interval. And so, we tend to want to go ahead and put that back in terms of one of those angles between 0 and 360, or I use our coterminal angle idea to make an adjustment there. So that may come up in an example or two. We'll talk about that. But otherwise, it's a pretty straightforward conversion as long as you watch the quadrant of your angle. So for example, say 5 plus 5i. And I want to convert that to trig form. Okay. Now, first thing, I'm just noting my quadrant. This is a point that is located in quadrant 1 because both A and B are positive 5. So we're in Q1. So that means my angle, theta, should be a Q1 angle. Find r as we did before. Right? So r is the square root of a squared plus b squared, 5 squared plus 5 squared in this case. So 25 plus 25, square root of 50. And then we could simplify, that's 25 times 2, right? So 5 square roots of 2. And there's r. And then again, I'll tell you I'd use tangent just to play with that a little bit. I've got tangent of theta is b over a, right? Y over x, b over a. So then I'm looking at a tangent of theta equal to 1, 5 over 5. And then we play our inverse game. Right? So I then look at the angle whose tangent is 1. And that's one of our recognizable angles, or should be by this point. If not, we're in deep trouble. But 45 degrees, or pi over 4. I mean, we're going to use radians, we're going to use degrees, we're going to use both here. Right? So there's no exclusive choice between degrees and radians. You'll see both used. So then I could take 5 plus 5i. There's r, 5 square roots of 2. There's theta, 45 degrees. And I can express this as 5 square roots of 2 cis 45 degrees. Here's the longer version. Like I said, that's the version you're going to have to use on MyMathLab. 5 square roots of 2 are r times the cosine of 45 degrees plus I sine of 45 degrees. Okay. But again, I'm just going to collapse that to cis, CIS, save you some writing. Number 2, I've got negative 10 square roots of 3 plus 10i. Right, so our a value is negative 10 square roots of 3. Our b is positive 10. So a is negative, b is positive. That puts us in quadrant 2. Okay. X is negative, y is positive. Now r, again, is always positive, so there's never any question about that. So I'm just plugging in a squared plus b squared, negative 10 square roots of 3 squared plus 10 squared. Negative 10 square roots of 3 squared. The negative 10 squared is 100. The square root of 3 squared is 3. So that would give us 100 times 3, or 300. And then we have 10 squared, which is 100. So I've got the square root of 400, which is 20. Ends up being a nice number in this case. Then we've got the tangent of theta equals b over a. So 10 over negative 10 square roots of 3. Or negative 1 over the square root of 3, or negative 3 over square root of 3 over 3 if we rationalize that denominator. And that's a recognizable value. Again, it better be at this point, at least in terms of our reference angle. The angle whose tangent is square root of 3 over 3 is pi over 6, or 30 degrees. So that's my reference angle. Now the fact that this is a negative tangent value, that should make sense because we said up here that this was an angle, or a point rather, that is in quadrant 2. So I'm going to use a quadrant 2 angle, and tangent is negative in quadrant 2 and quadrant 4. Right? So we want to identify the quadrant 2 angle whose tangent is negative square root of 3 over 3. If we use that reference angle, pi over 6 or 30 degrees, I'm going to go pi over 6 in this case. In quadrant 2, we take that reference angle, subtract it from pi, and that'll leave us with 5 pi over 6. There's theta. And so I've got my number, negative 10 roots of 3 plus 10i, being equivalent to 20. There's r. Cosine plus I sine 5 pi over 6. There's theta. Okay. Number 3 is just the number 4. And for this one, just kind of showing you a little bit of a shortcut, because like we keep talking about these numbers that are either pure real numbers or pure imaginary numbers are going to be numbers that lie on an axis. Right? So the pure imaginary, as we said, would lie on this imaginary axis. Well, the pure real numbers lie on the real axis. And in this case, it's just the real number 4. What is its absolute value? What is its distance from the origin? Well, it's 4 units. So there's r. R is 4. What is theta? Well, it's located on this positive x-axis, where theta would be either 0 or 0 degrees, right? 0 radians or 0 degrees, whichever one we need to use. So yeah, it just makes it a little bit quicker, a little bit more straightforward. I don't have to go through all the fancy formulas and calculations. If you just recognize the pure real or pure imaginary number lying on an axis, it's a little bit easier to find r and theta. So r equals 4, theta equals 0 radians or 0 degrees. So my complex number 4 in standard form has a trig form of 4 cis 0 degrees, or 4 cis 0 radians. Okay? So there is a way to write a real number in this trig format. All right, so that's converting. You don't know, throw me back up there every time. So that's converting from the standard notation to the trig notation. Going in the opposite direction, from the trig notation to the standard notation, this is actually the easier of the two. This is actually a little more straightforward. So converting a complex number from trig form to standard form, we're just going to make use of the fact that we said earlier, A is equal to R cosine theta, and B is equal to R sine theta. So I'm starting with the number that is in trig form. So I'm going to start with number 2, which is now number 1, 5 cis pi over 6. R is 5, theta is pi over 6, and we want to write that in standard form. I need to find A and B. So it tends to be a little more straightforward. A is R cosine theta, B is R sine theta. All right. Just jumping all over the place today. All right. So there's our 5 cis pi over 6, converting to standard form. Right, so just pretty straightforward. A equals R cosine theta, so A equals 5 times cosine of pi over 6. Cosine of pi over 6 is square root of 3 over 2. And there shouldn't be any issues there with sines or anything like that, because the angle is the angle. Right, so pi over 6 is in quadrant 1. Sine and cosine are both positive. Square root of 3 over 2 is our cosine, so I've got 5 times the square root of 3 over 2, or 5 square roots of 3 over 2. B is R sine theta, so B would be 5 times the sine of pi over 6. Sine of pi over 6 is 1/2. So I've got 5 times a half, or 5 halves. So there's my A value, 5 square roots of 3 over 2. There's our B value, 5 halves. So 5 cis pi over 6 in standard, in trig form, in standard form is 5 square roots of 3 over 2 plus 5 halves I. Number 2, the only difference there is we just have to watch our signs, SIGNs. So here I've got 6 cis 120. So there's A, R cosine theta. There's B, R sine theta. Now this is 120 degrees, which is in quadrant 2, where cosine is negative, sine is positive. My reference angle, if you want to make use of that, would be 60 degrees, right? So our cosine of 60 would be 1/2. In quadrant 2, that means negative 1/2. So here's R cosine of 120. Right? We said the alternative there is you memorize your way all the way around the unit circle. All right, but I use reference angles. My brain is getting old. I can't memorize stuff as well as I used to. So I just use reference angles and I figure it out. So I've got 6 times negative 1/2, or negative 3. There's my A value. Our B value, R sine theta. Again, this is 60 degrees is my reference angle, whose sine is square root of 3 over 2. And in quadrant 2, 120 degrees, sine is positive. So B is 6 times the square root of 3 over 2. We can simplify that, divide out the 2, and I've got 3 square roots of 3. So then our trig form, 6 cis 120. In standard form, A plus BI, negative 3 plus 3 square roots of 3I. So like I said again, that tends to be the more straightforward of the two in terms of the conversion. Next item up, more formulas. Multiplying and dividing complex numbers. Now, we're not going to do a whole bunch with this. You have maybe an example or two in your My Math Lab homework. But these are formulas. They're pretty straightforward. I'm looking at multiplying two complex numbers that are written in trig form. So if I take complex number R cosine plus I sine theta 1, second complex number r cosine plus I sine theta sub 2, and we multiply those two together. Here's our formula. We simply multiply the r values, and then we take the sum of the angles, right, or the arguments, remember we call them. So I've got the product of r sub 1 and r sub 2, cis, the sum of the arguments, theta 1 plus theta 2. Multiply absolute values, add the arguments. It's that straightforward. So for example, 5 cosine 60 plus I sine 60 degrees times 2 cosine 45 plus I sine 45 would simply be equal to the product of the r values, 5 times 2. And then the cosine plus I sine. I think I'll write this out a couple times just to remind us. Cosine plus I sine of the sum of the angles, 60 degrees and 45 degrees in this case. Cosine plus I sine, because I'm going to use that cis notation going forward, but again, I don't want you to forget what that actually means, because this is how you're going to have to put this into MyMathLab. So 5 times 2, I've got 10, and then I've got the cosine plus I sine of 60 plus 45, 105. And that would be the product of those two complex numbers. All right. But like I said, we're not going to do a bunch with that. That's how that works. Division, basically the same. All right, so we're going to divide the r values, divide those absolute values, and then this time we'll subtract the angles. We'll subtract the arguments. Right? Didn't want all of that. Right. So simply divide our r values, r sub 1 divided by r sub 2. And then we've got the cosine plus I sine of the difference of the angles, the difference of the arguments. Right? So r sub 1 over r sub 2, cosine of theta 1 minus theta 2. Now, of course, this is direction specific, so it's, as is always the case with division, it's the numerator, the angle in the numerator, minus the angle in the denominator. Right? But again, this is as straightforward as the multiplication. We're simply going to divide the r's. So I've got 15 divided by 3. And then we've got the cosine plus I sine of our angle in the numerator minus the angle in the denominator. And so I end up with 15 divided by 3, which is 5, cosine plus I sine of 46 degrees. Okay? So again, nothing real fancy there. Right, multiplication and division with complex numbers in standard form. That and $1 will get you a cup of coffee at McDonald's. Or I guess $5 at Starbucks. This we're a little more interested in. These powers of complex numbers and this use of what's called De Moivre's theorem. It's named after one of those famous dead mathematicians, De Moivre. I think he was French. So, yeah. This theorem has a couple of parts to it. It's both parts are dealing with powers of complex numbers. The first part is the easier part, the one we're looking at here, where I'm taking a complex number and I'm raising it to a power, where that exponent, the n value, is an integer. We call them natural numbers. That's a fancy word for the positive integers. They're called natural numbers. Right? 1, 2, 3, 4, 5, etc. Positive integer, natural number, same thing. So as long as I'm raising this number to a positive integer, the formula for calculating the value is to simply take the r, raise it to that power, that nth power. And then here we've got the cosine plus I sine of n times theta. Right? So obviously, again, I just want to make sure I'm not confusing or getting wires crossed between all these different formulas. Right? So when we're multiplying, we add the arguments. When we're dividing, we subtract the arguments. When we're raising it to a power, we multiply that exponent times the argument. All right? Now, the one issue here, though, is this formula does require that the number is written in trig form, right, using trig notation. So for our number 1, that makes that one a little bit straightforward. I've got the number 2 cosine 120 plus I sine 120 raised to the 4th power. So I'm just applying the formula. There's our 2 cis 120 to the 4th power. We'll simply raise 2 to the 4th. And then we've got the cosine plus I sine of n times theta. 4 times 120 in this case, or 480 degrees. Now 2 to the 4th is 16. And then there's our cosine plus I sine of 480. And then this goes back to what we mentioned earlier. I mean, there's nothing wrong with using 480 degrees as your angle. Perfectly fine. But we tend to gravitate back to the coterminal angle that's between 0 and 360. So 16 cis 480 degrees, 16 cis 120 degrees. It's the same number, right? We just tend to put it back in terms of that angle between 0 and 360. So use the 120. Okay? I mean, because like I said, ultimately there's any number of angles that would satisfy that would have the same value. Right? So we'll just try to stay a little consistent with that. Now, here's where the problem comes in. I say a problem. It's not really a problem. It just means more work. If the number is not in trig form to start with, I'm going to have to first convert it to trig form in order to use the shortcut, in order to use the formula. Now, in this case, I mean, it's a better form, because if I have this number in standard form, like square root of 3 over 2 plus 1/2 I raised to the 10th power, I mean, think of that like you would a binomial raised to the 10th power. When you're doing polynomials, that type of thing. You have x plus y raised to the 10th power. How do you multiply that out? You have to multiply x plus y times itself 10 times, right? Which is not really difficult, but it's time consuming. It takes a lot of time to do that. So the same thing here. So what de Moivre's theorem actually does, it allows us to streamline that process to where if I first take that number in standard form, in this case square root of 3 over 2 plus 1/2 I, and convert it to trig form, I can then apply de Moivre's theorem to raise it to the 10th power. Okay? So first, given a number in standard form, convert it to trig form. Now here's my note. Of course, I made a note that that number is in quadrant 1. Since I am going to be converting it to trig form, I want to make sure I'm identifying an angle in the appropriate quadrant. So here's our r, square root of a squared plus b squared. A is square root of 3 over 2, b is 1/2 in this case. Now square root of 3 over 2 squared, square root of 3 squared is 3, 2 squared is 4, so that's 3/4. 1/2 squared is 1/4, so that gives me square root of 3/4 plus 1/4, which is square root of 1, which is really about as convenient as you're going to get for an r value. Now, here's a little aside, just to go back to something we've talked about earlier in the semester. It should not be surprising that the r value here is 1. Because, remember, if we're taking this point, oops, let's switch to my pen. If we take this point and plot it in the real number, in the complex number system, all right, square root of 3 over 2 is my a, 1/2 is my b, or square root of 3 over 2 is my x, 1/2 is my y. That would put us a point out here whose coordinates are square root of 3 over 2, 1/2. That should look familiar. That's a point on our unit circle, right? And it's actually the point that lies on an angle whose measure is 30 degrees, or pi over 6, right? So, and if you recognize that, great. If not, no big deal. We can still go through the calculations to get everything else that we need. But I just wanted to point that out to you. I mean, the fact that you've got square root of 3 over 2 and 1/2 as the coordinates of your point, the fact that r is 1, that's not by coincidence. I mean, that's a point on the unit circle whose radius is 1, right? So, yeah, I'm kind of tying some different things together. But there's r. R is 1. So then we said tangent I could use, or sine or cosine. Like I said, any one of the three, however you want to get to your angle. And like I said, if you recognize that that's 30 degrees from the get-go because of those coordinates, that's fine. Otherwise, go through the calculation. So I've got tangent of b over a, 1/2 over the square root of 3 over 2, which would be 1/2 times the reciprocal, right? 2 over the square root of 3. So that'll give us 1 over the square root of 3, or again, the square root of 3 over 3. And then I've got the angle whose tangent is square root of 3 over 3 in quadrant 1. Because we set up here that our angle would be a quadrant 1 angle. So there's our 30-degree angle. Or again, pi over 6. You'll see both. So this number, square root of 3 over 2 plus 1/2 I, can then be written in trig form as r cis theta, 1 cis 30 degrees. Of course, you don't have to write the 1. I'm going to leave it there just to emphasize that there is an r value. Okay. But now, everything that we've done there has nothing to do with what we're raising the number to the 10th power. Right? That has nothing to do with de Moivre's theorem. That's just all about taking the original number and converting it to trig form so that we could then use de Moivre's theorem. Right? So now that I have it in r cis theta form, r cosine plus I sine theta form, then we can take our number 1 cis 30 degrees and raise it to the 10th power using the formula, using de Moivre's theorem, which says it will take r and raise it to the n power, so 1 to the 10th. And then we've got cosine plus I sine theta of r of n times theta, so 10 times 30 degrees. So that gives me 1 cis 300 degrees. That is the 10th power of 1 cis 30 degrees. Now, we started off with a number that was in standard form, square root of 3 over 2 plus 1/2 I. This is that number raised to the 10th power, but it's in trig form. So we may need to be, or we may be asked to convert it back to standard form. It's just a matter of what's asked in our question. But quite often, when you're given a number originally in standard form, like we are here, we convert it to trig form so that we can easily raise it to whatever our power is. But then once we have that, we're going to then convert it back to standard form if it's convenient to do so. Right? And in this case, it is. So we're going to convert it back to standard form. Right? And so that's the easier conversion anyway. A is r cosine theta, b is r sine theta. Find a and b. So in this case, it's 1 cosine of 300 and 1 sine of 300. Now 300 is quadrant 4, where cosine is positive, sine is negative. Our reference angle there is 60 degrees, 360 minus 300. And so our cosine of 60 degrees, 1/2. Our sine of 60 degrees, square root of 3 over 2. But then we're in quadrant 4 with our angle, 300 degrees, where we said cosine is positive, so positive 1/2. Sine, however, is negative, so negative square root of 3 over 2. So A is 1 times 1/2, or 1/2. B is 1 times negative root 3 over 2, or negative square root of 3 over 2. There then is our number to the 10th power, but now in standard form. So square root of 3 over 2 plus 1/2 I to the 10th power is equal to 1/2 minus square root of 3 over 2 I. Right? So again, it's not the formula, it's not de Moivre's theorem there that's the problem, it's the conversion back and forth between the two forms. That's the bulk of the work. Okay? Now, this last part, this is the fun part. You're going to love this. Back to the beginning. Come on. So this is the second part of de Moivre's theorem, where the first part was raising numbers to powers, where the exponent was a natural number or a positive integer. Here I'm also raising numbers to powers, but the powers that we're talking about here are roots, like square roots, cube roots, etc. Within the real number system, right, before we get to the complex numbers, just a quick review, refresh. Within the real number system, you talk about a square root of a number. We always say that there's 2 square roots of a number. There's a positive square root and there's a negative square root. So every positive number has 2 square roots. How many cube roots does a number have if it's just a real number? The number 8, for example, is 2 cubed. So 2 is the cube root of 8, but it's the only one within the real number system. Negative 8 is negative 2 cubed. So the cube root of negative 8 is negative 2, right? But it's the only cube root within the real number system. Now, if you expand your number system to include the complex number system, so we bring in the imaginary numbers as well, then it turns out that within the complex number system, every non-zero complex number has 2 square roots. That's nothing new. That was the same for real numbers. But it also has 3 cube roots and 4 fourth roots and 5 fifth roots, etc., etc., etc. So in this case, I'm raising it to the 1 over n power. Because remember, when you write square root, you could equivalently write that as raising that radicand to the 1/2 power. Square root of x is x to the 1/2, or cube root of x is x to the 1/3, right? That equivalent exponential notation. So I'm looking at an exponent again here, but it's an exponent of the form 1 over n. So if I'm looking at a square root, it's 1/2, a cube root is 1/3, a fourth root is 1/4, etc., etc. Okay? So this part of De Moivre's theorem says that the nth roots of a complex number, r cosine plus I sine theta, is given by this formula. Now this is a fancier little formula. There's a few moving parts to it. So, and as I said, this is probably why this is a little more interesting, because of the formula that you're going to have to remember. I can raise that number to the power by taking the r, raising it to the 1 over n power, times the cosine plus I sine of, we're all over the place with this one, theta over n plus k times 360 over n. That's ugly. I don't like that. Yeah. So theta over n plus k times 360 over n, right, in the case of both cosine and the I sine. Now, what is this k value? The k value always starts at 0 and goes up to n minus 1. So in other words, if I'm looking for, say, the fourth roots of a number, I know there's 4 of them. We use the formula and we plug in the different k values, because n would be 4, whatever that root is. And then k will start off at 0, and I would have k equals 0, k equals 1, k equals 2, and k equals 3 to give us the 4 fourth roots of that number. All right. But again, it's a formula. Right? The only thing that changes is k. The n is going to be fixed once we're told what our root is. The rest of it is just plugging in different k values. So again, even though it's a little fancier formula, it's not a difficult formula. Yeah, like we always say with formula, as long as you know the formula, it's an easy formula to use. All right, so it's like anything else. So let's say, for example, if I'm looking for the square roots of 1 plus I, now again, I'm always interested in quadrants. Keep track of that. We're in quadrant 1 with 1 plus I. Both A and B are 1 positive. But same issue we had with the previous problem. If we're going to use the theorem, if we're going to use the formula, we have to put the number into trig form first. We have to have it in the cosine plus I sine form first in order to use the formula. So we need to find r, we need to find theta. So r in this case, with a and b both equal to 1, square root of 1 squared plus 1 squared, or square root of 2. I've got the tangent of theta, which would be 1 over 1, or 1. And so again, there's our 45-degree angle, right? The angle whose tangent is 1 in quadrant 1 is 45 degrees. So 1 plus I in trig form would be written as r cis theta, square root of 2 cis 45 degrees. And then we're looking for the square roots of that number. So again, all I did was convert from standard form to trig form so that I could use the formula. So we're looking for the square roots, which means n is 2. So then here's our formula. It's r raised to the 1 over n. Let me maybe rewrite that underneath here again. It's r raised to the 1 over n times the cosine plus I sine of theta over n plus k times 360 over n. Or 2 pi over n. You know, we could do radians as well. Watch it all my parentheses and then the big bracket. Right? That's our formula that we had on the slide. So I'm just plugging in my n value and r value to start this off. So I've got r to the 1 over n, square root of 2 over, or raised to the 1/2 power. And then here's our cosine plus I sine of theta over n. Theta was 45, n was 2, plus k times 360 over n, 360 over 2. And again, it's the same in both parts of that. So that's why we just use the cis notation. So now look what I did with the square root of 2 to the 1/2, because we could simplify that. Square root of 2 is 2 to the 1/2. Right? So I'm just rewrote that as 2 to the 1/2. And then again, it's raised to the 1/2. Here's our cosine plus I sine of 45 over 2, 22.5 degrees, plus k times 360 over 2, which is 180 degrees. And then for our roots, we plug in the k values, k equals 0 and k equals 1, to get the 2 square roots. And so our first root, now that's 2 to the 1/2 to the 1/2, right? Power to a power we multiply. So that gives us 2 to the 1/4. Here's our cosine plus I sine, 22.5 plus 0 times 180 degrees, right? So plugging in 0 for k. Now notice, of course, and that's going to be the same for every one of these that you do, because the first root, k is 0, it's just always going to knock out this back end of the formula, right? So I'm really just left with the first root being the cis of theta over n, right? So 2 to the 1/4 cosine plus I sine, 22.5 degrees. There's our first root. And then for the second root, we'll plug in k equals 1. So again, it's still 2 to the 1/4. That doesn't change. And then it's cosine plus I sine of the 22.5, but this time plus 1 times 180, or 180 degrees. And so 22.5 plus 180 is 202.5 degrees. So I've got 2 to the 1/4 cis 202.5 degrees, cosine plus I sine. Yeah, so I mean, it's a formula. It's just an ugly formula, but it's like any other formula. Know the formula, plug in the values. Number 2, we're looking for the cube roots of negative 64i. That at least makes it a little bit easier to find r and theta, because when we talked earlier about the purely imaginary number, negative 64i is purely imaginary. So if we were to plot that in that complex plane, right, it would be plotted on that negative imaginary axis. So r, which is again the absolute value of that number, right, is always positive. Distance from the origin would be 64, so r is 64. Theta is 270 degrees, right down there on the negative imaginary axis, 270 degrees. So there's r, there's theta, so negative 64i in trig form would be r cosine plus I sine theta, 64 cis 270 degrees. And then we're looking for the cube roots of that number, which then there would be 3. N equals 3. There are 3 cube roots. We start again with k equals 0, and then 1, and then 2. Always up to n minus 1. So then our formula, there's r to the 1 over n, so 64 to the 1/3. There's our cosine plus I sine of theta over n. Back to my little formula up there. Theta over n plus 300 k times 360 degrees over n where n is 3 in this case. So I've got, now notice that's 4, well that's the cube root of 64, right? 64 to the 1/3. That's the cube root of 64, which is 4. Always want to simplify when we can. Cosine plus I sine, there's our 270 divided by 3, which is 90, plus k times 360 over 3, which would be 120. And then we just plug in the values for k. For k equals 0, like we said, that's just going to knock off the second half of that formula. I end up with 4 cosine plus I sine 90 degrees. There's our first root. And then just notice for the others, all we're going to do from that point forward is just add multiples 120 degrees, right? Because we're just increasing k by 1 each time. So when k equals 1, I'm going to add 120 degrees to that 90 to get to 10. And then for k equals 2, I'm adding 240 to the 90, or I'm just adding another 120 to the previous. Either way, I've got 330 degrees. Now that would be the trig form of those numbers. If we needed to convert them back to standard form, we could do that, right? We've done enough of those already, so a lot of times with these, we tend to just leave them in trig form, especially when you have multiple roots, so you don't have to go through and convert every single one of those to standard form. It's a little more common just to leave them in trig form. But that's de Moivre's theorem. That's raising complex numbers to powers and finding roots of complex numbers. That's it for that section, 8.3.